In this section, we're going to be carrying out hypothesis tests with samples drawn from a population which is assumed to be normal. Consider this normal distribution here. We know that normal distributions are symmetric. This one has a mean mu, and the standard deviation is sigma. If x is a random variable following this distribution, we say that x follows a normal distribution with mean mu and variance sigma squared. This distribution holds for single readings taken from this distribution. We know that the probability is highest that we get a value towards the middle, and lower as we move away. But consider taking a sample, let's just say of size 5, from this population. Taking a sample of 5, we might get a value here, 1 here, 1 here, 1 here, and 1 here. The mean for these may well be here, quite close to the actual mean. It's very unlikely that we'll end up with 5 values that are as far out as this one or further. So the chance of the mean for this sample being out here is going to be less than the probability of one individual value being here. Let's suppose we take lots and lots of samples of size 5, and then we take the mean of these samples, and then work out the mean of all of the means from the samples. We'd expect that to be here. All of the samples are drawn from this population. Therefore, on average, we expect the mean to be the population mean. But as we just discussed, we'd expect these means to be in closer to the population mean than for a particular individual value. That means the shape of the distribution for the samples would have the same mean, but a lower standard deviation. This idea is central to what we'll be doing. Let's suppose we took samples of size n. With no justification, I'm going to tell you that the mean of the x's in samples of size n is normally distributed mu, and the variance is sigma squared over n. The standard deviation for this is the square root of the variance, so that's sigma over root n, and that's given a special name. It's called the standard error.